So this is inverses of exponential functions, which we talked about yesterday. What's the inverse of an exponential? Logs. So we're really just talking about logs. And this is going on page 67 when we're done. That's not even 67. That's 67. So that doesn't even make any sense. Y'all are dorks. So silly, so silly. Okay. I paused it for that, yeah. I need to put all that out there. Okay, we got to act like we're actually serious around here sometimes. Well, it was last period. I have a lot of sophomores in that class, and so they were like, they giggled, and I was like, "What is so funny?" And then it dawned on me because they were just laughing. Third period, I guess they're not awake yet. I don't know. So, but no, I did not get a round of applause and the rest. So, I guess if I need to feel good about myself, I can just say that number, and then people give me a round of applause. Did you miss us? Oh my God, thank you. Okay. So it says, just as we can graph previous functions, we can also graph logs. We'll actually, I don't know why that sentence is at the beginning because we'll do that in just a minute. But here's the general form for a log. Yesterday we talked about log having a base and an argument, but this one has an a in front of it for a transformation. What does the a do in transformation wise? It's a dilation. What kind? Vertical. Good. So it's a vertical dilation, which is just going to stretch it vertically. But notice it says b has to be greater than 0. So your base, the base of a log, it cannot be 0, and it can't. Or I'm sorry, not that it can't. Well, it can't be 0. It has to be greater than 0. Sorry, which means it can't be 0. But not only does it have to be greater than 0, it also can't be 1. So it can be between 0 and 1. It can be 0.5, and it can be 1.5, but it can't be 1. And a can't be 0, because if a is 0, then the whole thing's 0, right? And it just doesn't make any sense. But so no negative bases is not going to work. All right, so then because exponential functions and logarithmic functions are inverses of each other, we would expect the characteristics of input-output values of exponentials and log to switch places, which they do, just like everything else does with inverses. So inverses was either from 2.7 or 2.8. It was those ones you're quizzed on next week. One of those two was inverses. So we've already talked about them. I also know for a fact, well, I know without this, but I know that they're not brand new. But not only that, pre-AP Algebra 2, that's literally what they're doing right now. So we're kind of doing the same thing. But I don't think they're talking about logs right now, but they're talking about inverses. And just really inverses, the same kind of properties work for all of the functions. So this says recall, which means, remember, we talked about this already. We talked about this last semester. For exponential functions over equal with input value intervals, which I know you've heard that and written that phrase multiple times, although I was using over equal length input value intervals, but it means the same thing. Whether you say equal length or equal width, it does not matter. The output values change multiplicatively. That is your $10 word for the day, okay? Multiplicatively is just a really fancy way to say something's being multiplied, okay? Another way to say that it is changing multiplicatively would be to say that it is changing proportionally, which is a longer word, but doesn't sound as, well, it might be longer, about the same length, but doesn't sound as complicated as multiplicatively, right? Okay, so what we know about exponentials, or what we do for all of these functions that we've been doing, is we first look at our input values. And we see that our input, we have equal length input value intervals, right? We're adding 2 each time. Then our output values here, we are multiplying by 2. And that's what indicates that we have an exponential. That's something that we need to be able to recognize. And it says, notice how the input values are changed. So inputs are changing additively. That's another way of saying equally spaced, or we're adding the same number every time, or equal length input value intervals. All those mean the same thing. While output values are changing multiplicatively. That's indicative of an exponential function, okay? So we're going to use some words here. Here's good news and bad news, is that the good news is that you're not actually going to have to write this stuff out on the AP exam. It is multiple choice questions. But the bad news is there's at least 3 different ways they could state the exact same thing. So you just have to know that they mean the same thing. So when we write these answers down out here at the bottom, I'm going to write each one of them in a different way so you can see that it's the same thing. On the key to the assignment, I'm only writing it one way. And I think you will be able to recognize whether or not you're saying the same thing in a different way, okay? Because I'm not going to write it out every single different way it could be. But that'll probably make sense a little bit more when we get there. That's why we need to know that multiplicatively means proportionally, which means just being multiplied by the same thing over and over again. And that additively means equally spaced or equal length input value intervals, or adding the same thing every time. They all mean the same thing. And so I'm going to write them different ways so you're not surprised by any of the language, because I can't tell you for sure what it's going to look like. It could be anything. All right, but all that makes sense for exponentials, right? So we know that logs are just the inverse. So if I take that table there and I reverse x and y, then I have this logarithmic function. These two properties of input and output values are reversed. So here, my inputs, these are the only ones where we don't want equal length input value intervals. Here, the inputs are changing multiplicatively, and our outputs are changing additively. Those properties switch just like the numbers switched, okay? And that's basically what this says. Input values changing multiplicatively, outputs changing additively. Okay. So I will help you with the words down here, but I'm going to give you a minute, and at your tables, I want you to talk about A and B and decide at your table if those two, we'll talk about C and D in a minute, if the functions could be logarithmic, exponential, or neither. Okay, and I want you to be able to tell me why, but you don't necessarily have to say it in fancy words. I'll help you get the fancy words down. Okay, so go ahead and talk about it amongst yourselves, and then I'm going to call on somebody to volunteer to help me.
Okay, so B is log and this one's exponential.
And Amanda just gave everybody the answers. I'm just kidding.
You're welcome. You're welcome.
Make sure you can explain the why behind it if I call on you.
We're not doing these two. We're only doing A and B.
Okay, but how do you know?
One person raised two.
Sorry, whoa. 3 plus 1 is 4. 16 divided by 2 is 8. 8 divided by 2 is 4.
That's how this one's exponential.
Okay, but why is that log?
Because your x is being multiplied with these plus.
Okay, that's all I need.
Yeah. See, your x
Okay, are we good on A and B? All right, let's see who my first volunteer is. Paulina on A. Where are you? There you are. What does your team think about this one? Exponential. Okay, why? Beautiful. So this is exponential. And here we can see that we're adding 1 each time, which means we have equal length input value intervals. And she said they're changing additively. Same thing, beautifully said. Then here, they're divided by 2, but she said changing multiplicatively. Have we talked about division at all yet? No, because yes, I know that you see, and it's being divided, but we have to talk about it multiplicatively. So what is it being multiplied by? No, 1/2, -2. Okay, all right, does that make sense? So even though it may look like, and yes, we could say, I mean, yeah, obviously it's also being divided, but the rules are all about addition and multiplication. Okay, so I'm going to write this one out pretty much exactly like what she just said. Exponential, and instead of saying input values, which is fine, and which what I'll probably say, if we just say inputs, it kind of takes care of it. We don't have to write as much. So inputs change additively, and outputs change multiplicatively. And here's some other good news. This is a math test. So on the stuff you do have to write out, as long as you spell it correctly enough for whoever's grading it to figure out what the heck you're trying to say, it's okay if it's not spelled right. If you spell it so wrong it means something else, that's a different story. But you just do your best and then it's totally fine. Okay? We good? Does this make sense to you? Yes? Okay. So when I call on somebody for B, I challenge you to give me an explanation, but say it differently than what she said. Like, don't use the words additively and multiplicatively. Try to use some other words, and let's see what happens here. All right, so my next volunteer will be Kayla. Kayla, what did your team think about this one? Did y'all talk? Y'all didn't talk? There's 5 of you there. None of y'all can talk? Do what? Logarithmic. Okay, so he's going to help you out. Logarithmic. All right. Can you tell me why there? Go ahead. Okay, yes. Do they change? So yes, they change exponentially. But we can't use those words because it's kind of like using the word in the definition. So they change, and you're right, because it is an exponential change, but how else could you describe the change? What's happening each time? Being multiplied by what? 3. Okay, so you can say it's being multiplied by 3. Okay, or changing multiplicatively or being multiplied by 3, because it's really the change is multiplying. The change isn't exponential. Does that make sense to you? Okay, good though. Thank you very much. And then this is changing additively. All right, I'm going to change up the words just a little bit because, again, I'm going to try and write these a little bit differently each time. So I'm going to go with we'll just say that the inputs are multiplied by 3. And outputs add 10. That's probably the least likely way you would see it, but it doesn't mean that it wouldn't happen, or it doesn't mean that it wouldn't say like inputs are multiplied by 3 and output values are equal length input value or equal length output value intervals, right? They can kind of mix them. So I'm just kind of doing, whatever there. Okay, we all good on those? Any questions? All right, then C and D. I'll give you a minute to think about talk about those. Y'all actually talk this time, okay?
Multiplied by 1/2. Wait. No. I said never mind. I said never mind.
It is logarithmic. Being multiplied by 10. And then the second one is also logarithmic. I thought it was like what's wrong?
I'm a liar.
Well, okay, neither's an option. I feel like it's there for a reason.
Neither's an option.
Why is neither? I hate when they make neither.
Exactly.
Multiplied by 2 here.
This side it's B.
That's why it would be neither. I ran neither.
Come on. Yeah.
I feel like you just started what? The week? I know. That's okay. We're not going to complain that it's Friday.
Can you have a negative
Yeah, well, 4 days next week.
It's plus 10.
All right, have we fought it out? You think?
I've never seen negative log. Okay, let's go.
Yeah, there's a lot of things we've never seen. Good point. Okay, how many logs have you seen? All right, Yamalex. Did y'all talk this time? What did you think about this one? Okay. Okay. So do we think it's logarithmic, exponential, or neither? Yeah, she's over there shaking her head. Well, if it's going to be exponential, then the outputs change by being multiplied, but the inputs have to change additively, right? And if it's log, the outputs have to be additively. Since they're both multiplied, you would think it would be what? Neither. Very good. To be neither. And then again, just to kind of change up the words a little bit, I'm going to say inputs and outputs both change proportionally. And see, if I wasn't using my random thing over here, that table would probably think I'm picking on them because they didn't talk the first time. Okay. But I'm not. All right. Even though I might have if I didn't have this. All right, Nunu. What do we think about D? What did your table say about D? Or you, okay, go ahead.
X is multiplied by 2.
Okay.
And then the other one is subtracted by 3.
Okay. Can we subtract though? What are we doing?
Adding
We're
negative
adding, good. We're adding -3. Good. All right, so what do we think? What kind? Logarithmic. Okay. Y'all agree with that? Okay, so these words, this is what I'm going to say. I'm going to say inputs change multiplicatively, because I like that word, multiplicatively. And this is probably the only time that I would ever actually use it in a sentence. So inputs change multiplicatively over equal length output. Oh, output. Goodness, that says out. That does not look like output. Hang on. I know it looks like output. So equal length output value intervals. Ugh. Intervals. I don't know. Everybody okay with that? So do you see how we can say it different, but it means the same thing? So again, as long as you can recognize it, I don't want any of these words or these phrases to be surprises for you. I think you'll be able to handle it just fine. Okay? Any questions at all? All right, beautiful. Let's flip it over. Okay. Notice that this exponential is just b to the x. It's not a times b to the x. We have no a there. We also have no a here, okay, because that would be a transformation. So these are the parent functions before any transformations. If you've got the bases are the same and the exponent and the argument are the same, then they are inverses of each other. This statement right here is true for any inverse, not just log and exponential. Okay, and we did that when we did inverses. F of g of x equals g of f of x, right? Two important properties of inverse functions. Again, inverses in general. Graphs of inverse functions are reflections of each other over the line y equals x. Remember that? So we have, if I have an exponential right here, then this, if there's no transformations, it's a parent function. What is the y-intercept every time? 0. 0? That's a 0? Your input is 0. What's your output? 1. Because if my input is 0, anything to the 0 power is 1, right? So no matter what the base is, 5 to the x, 6 to the x, 1,000,000 to the x, that y-intercept right there will be 1 no matter what. Okay? That's an important thing for you to keep in your mind. Now, then if I have here's my line y equals x, and I can reflect in that line, that's what my parent function of a log looks like. So guess what that x-intercept is every time? 1. So just like we think about the rest of the unit circle through the first quadrant, because that makes the most sense to us, exponentials will probably always make more sense to you than logs do because you've known them longer. You've been doing them since Algebra 1. So if you can make sense of the exponential stuff and tie it to the log stuff, then the log stuff isn't that bad. Okay, we good on that? All right. And then the other thing, and this again is true for every inverse, if the point xy is on the graph of f, then yx is on the graph of f inverse because we're just switching them, right? All right, so one of the other things we did with inverses was to show that they were inverses by doing this right here, f of g of x and g of f of x. So when we do this, we're going to review a few properties before we actually review the properties. So I've got f of x and g of x, and it tells me to show. It's not asking if they are, so that means they are, and I got to show that they are. So we're going to start with f of g of x. So I'm going to take g of x, put it in here. That means I get 3 to the log base 3 of x power. So that log base 3 of x is all up there in the exponent. If I have the base of the exponential and the base of this log that's in the exponent are the same, and there's nothing else going on, no number in front of the log, no number in front of 3, whatever, then these essentially, not the same way as division, there's math behind it, but these two kind of cancel each other out, and it just equals x every time. Okay? I will show you the why behind that after we review some properties. I'll show you the why behind this one now because I think you'll remember the properties. If I do g of f of x, this goes into here. So I'm going to get log base 3 of 3 to the x power. The same thing, it works kind of the same way here. Log base 3 of 3 to the x, there's nothing extra going on here. This base and this base are the same. So these essentially cancel out and you're left with x. Here's the why on that one. This log base 3 of 3 to the x. You have a property, and I know it's been a hot minute since you've done them, but there is a log property where you take, if the exponent, if you have the log of an exponential, the exponent gets to come out front, and this becomes x times log base 3 of 3. Does that at least look a little familiar? Like you remember doing it, even if you don't remember all the properties? And then this is multiplication here. But then if you have the log of the base of the log and the argument are the same, then this always equals 1, and that's 1 times x, which is where you get that x. But just knowing that they kind of cancel out, you can skip those steps every time. You don't have to go through the process every time. Okay? And we'll go over the properties more. This is just showing you that they really are inverses. Okay? Everybody good so far? Beautiful. So let's look at the graph, which we already talked about the graph a little bit. But we've got a portion of k of x is 2 to the x. Sketch a picture of k inverse on the same coordinate grid. Okay, so I can see that I have this point 0, 1, so I can go to 1, 0, just like we talked about over there, right? I also have a point 1, 2, so that becomes 2, 1. I would like a point from the left-hand side of the y-axis, but they're all between 0 and 1, and I don't want to have to guess. So since I don't want to have to guess, I want to actually think about what this point right there is. X is negative 1. So if I do k of negative 1, that's 2 to the negative 1 power. What is that? 1 over 2. So that means that ordered pair right there is negative 1, 1/2. So for the inverse, that's going to be 1/2 negative 1, and I get a point right there. Okay? And then we just do our best to make a halfway decent sketch. Oh, not like that. Goodness, hang on. A little carried away there. Yeah. Pretend like I hit that point. I'm not doing it again. Yeah, 1/2 negative 1. Because also remember that you have a horizontal asymptote at y equals 0 for your exponential. That means you have a vertical asymptote at x equals 0 for your log. Okay? Yeah, your asymptote. Okay. All right, any questions? And again, on the actual exam, and even on probably most all of my exams, you're not going to have to actually graph, but to understand this stuff, it does help us to actually graph them and understand the graphs on the notes. Okay, example 4 here. The exponential function h of x equals a. So I got an exponential right here. It contains these points, right? So I have, well, I'll just write it right here. So my exponential looks like this. This is h of x, right? Then I want to find the average rate of change of the log function over this interval. Here's my log function. If this is h, what is this? Inverse of h, so it's h inverse of x. Okay. Everybody with me on that? So here, these points go with h. Am I going to use those points to find my average rate of change? No, because I don't want the average rate of change, right, of h. What do I want the average rate of change of? H inverse. So what would my ordered pairs be for H inverse? 3, 2, and 27, 6. Now, just to be clear, because there was some confusion about this, it's not that we're not finding the average rate of change of H because we can't, because it's exponential. It's because nobody asked us for it. We can find it, we just don't need to. These are the points I'm using to find the average rate of change on this interval right here. So I'm going to give you a minute. I want you to do that at your tables, and don't forget your function notation. And while y'all are working on that, I'm going to pass out your assignment from today and yesterday. Function notation, ask each other, talk to your peeps, see what you can figure out. It's important. Lots of you missed lots of points last semester because of that.
I didn't know. Me too. So we do, how does it work? We go the inverse first. What did you find the slope?
You put the y, x first over y. Wait, I thought you put y over x. Isn't that flipped?
Y'all fight about it. I don't know. Why is he the only one actually doing any work right now? Be more like him. I see a lot of slope going on. I don't see a lot of function notation going on. And I will be back with another pink one in just a second. No, that's just labeling.
Oh, it's just right now.
Okay. If I'm going to find the average rate of change, I know I'm going to start with a fraction. Do I start off by just putting numbers in the numerator? No. What do I write in the numerator? H inverse of what? 27, thank you very much, minus H inverse of 3 over 27 over 3. It's like I'm talking to myself up here half the time. So many of you missed so many points on things and still haven't learned your lesson. That is setting it up in function notation. And it's H inverse, not H, because I think some of y'all did write H. You were at least on the right track there. When you start average rate of change, it makes absolutely no difference what the actual points actually are. All you need is that interval, and you can get that first step done. Okay, that is doing average rate of change in function notation. It's not just 7th grade slope. I mean, it is, but you got to dress it up a little bit with your function notation. Then your next step, what is H inverse of 27. Okay, 6. So this is 6 minus 2 over 27 minus 3 is 24. So I get 4 over 24, which is 1/6. There is more to math than getting the right number in the end. Process is important. It makes no difference if you can't start it right. Okay? Any questions at all? We good? Awesome.